Hello, we are now off to Chapter 3. Chapter 3 introduces us to vector-valued function. Well, actually, we've already been studying vector-valued functions in 2 dimensions when we studied parametric equations back at the beginning of the semester. But now we're going to look at these parametric equations in both 2 and 3 dimensions. And we are going to refer to them from now on as vector-valued functions. If we essentially package your x and your y and your z values together, then we have this vector-valued function. All right. So in our first section, vector-valued functions, we're going to define them, and then we're going to do a little bit of limits and continuity. So the definition of a vector-valued function is essentially a function that has 2 or 3 components, and each of these components will have a function of t, function of one variable in them. So we're saying that the functions in the third dimensional case is f, g, and h, and they're all real functions with parameter t. And sometimes we can write the vector-valued functions using the standard unit vectors, ij or ijk, or we can write them in our angle notation, angle bracket notation. The domain of a vector-valued function is going to be an interval or pieces of an interval from a real number, and it could be all real numbers or just a subset, just like we've studied back in pre-calculus. The range are going to be functions, are going to be vectors or points, but they're called vector-valued functions, so let's just say that they're going to be vectors whose tails are at the origin, and they will be pointing at the points in 2 or 3-dimensional space. So here's an example of a vector-valued function. They're asking us to find r of 0, r1, and r of -4. So just like any other function that we've seen before, we're simply going to be putting the values for t into this vector-valued function. So r of 0, for example, is going to be 0 squared minus 3 times 0 in the I direction, plus 4 times 0 plus 1 in the j direction. So this is going to be 0 in the I and then 1 in the j. So that's just j. We can also write this vector-valued function as a vector with angle brackets. So t squared minus 3t, comma 4t plus 1. So let's do the next problem where we find r of 1, and that's going to be 1 squared minus 3 times 1, comma 4 times 1 plus 1. So this is going to be -2, comma 5. All right. So we get the idea. Let's do this one more. This is -4 squared. That's -4 in parentheses. Let's just write it out just in case. Minus 3 times 4, 4 times -4 plus 1. So this will give us 16 minus 12. That's positive 16. Minus 12 is going to be 4. And then this is -16 plus 1 is -15. Okay, so it's your basic input-output structure now. And we have it in vector form. Now, finding the domain of a vector-valued function is essentially finding the domain of each of these functions. So let's start with finding the domain of t squared, comma tan t, and ln t. So the domain of this is the t squared is going to be all real numbers. The tangent function, if you remember, has discontinuities at pi over 2, and then 3 pi over 2, and negative pi over 2. So they kind of look like a bunch of curves like that. And so this is going to be all real numbers, except, let's say t equals pi over 2, and then plus or minus n pi, where n is going to be in any integer. So the symbol for integer is just z symbol, or just say integer. So now between these two functions so far, it's going to be all real numbers except for pi over 2 and any multiple of that. Now this one, the lnt, if you remember, exists only in the positive part, not just positive, yes, positive t is bigger than 0. Okay, so now we want to combine all these together. We will have all real numbers, okay? We'll have t is bigger than 0, so we know it's going to be t is bigger than 0, and then we have to eliminate all these pi over 2 multiples. So your domain here can be set as t bigger than 0, and t does not equal to pi over 2 plus n pi. Now, when n is negative, then it doesn't matter because t has to be bigger than 0, so we're not going to go to the negative side. So technically, we're really just looking at positive values for n, but I don't think we need to specify that. We can just say that it has to be bigger than 0 and not including any of these. All right. Now, a graphs of these things we may have seen before is going to be the set of all t values, and for each t values you have the r of t, which in 2 dimensions would have an x component and a y component, or in 3 dimensions you would have an x, y, z component. Now, if you're in 2 dimensions, we call that a plane curve, as in happening on the xy plane. And then if you're doing this in 3 dimensions, you're looking at a space curve, or a curve in 3-dimensional space. And it says here, any representation of plane curve or space curve using vector valued functions is called a vector parameterization. All right, so those are just some definitions. Let's take a look at an example. Much like the parametric equations that we studied, we could make up a table of t, and then here, since this example has 3 dimensions, you can imagine plotting points x, y, and z. Now, we're not going to plot points here because it could get really complicated, but we can try to figure out how these things might look like. This particular example has an interesting x and y component, and if we kind of eliminate this k component for right now and just look at what's happening in R2, if you remember this is x is equal to cosine t, y is equal to sine t, and that's just a unit circle going in a counterclockwise direction. And if we want to be specific, well, t starts at 0, we'll be at the point 1, 0, and it's going to go around by the time we get to 2 pi. Now imagine putting this now in 3 dimensions, where the shadow of this curve is just going to be in the xy plane. That's what the circle is, and that's the shadow. Now, if we throw in this third component, z, at each time we move along the t-axis, we're going to be growing in the z-axis, so we're going to be going up and up in the z-axis. So you can imagine starting from here, and then it's going to be lifting off. Looking at it from the top, it looks like it's still drawing a circle, but if we look at it from a three-dimensional perspective, it's going up in the z-axis, in the z direction. So we have what we would call a helix. Now, if we take a look at a plotter, since we should take advantage of looking at these graphs. One of the options here is the space curve, and then here's cosine. So it's pretty close. Their default example for a space curve is the helix. They have 0.1 in for t, but we'll put in 0.2, which is our problem. And for now, let's just go from 0 to 2 pi like we were discussing. And then we see something like this. So it goes up around. If we extend this negative 2 pi or make this go up to 4 pi, we get more and more of that helix. Now, if you look at it from the top, you just see that circle that we had mentioned. But then if we look at it from a three-dimensional perspective, we see that it actually goes up. Okay. Now, if we imagine looking at this as a vector-valued function where the output is a vector, and then that you can imagine that that vector is tracing out a point as we go up along this. As we increase our t values, our x, y, z value changes according to that circle and the z going up. And so we have this helix being drawn out by the vector. Again, different perspectives. From a two-dimensional perspective, we just see it's going in a counterclockwise direction. And in a three-dimensional perspective, from different angles or different points of view, you can see how it's moving. Okay. All right. A couple more objectives in this particular section. We're looking at limits and continuity. So this is the definition of our limits. A limit is going to be a result of a vector, or the resulting thing that we get from a limit is a vector, because it is a vector-valued function. And so this thing should be approaching some sort of vector. And so we say that limit as t approaches a of some function r of t is going to be a vector L, given that the magnitude of the difference between r of t and L is going to approach 0. It's going to get closer and closer to 0. That seems pretty technical, but if we remember limits back in Calculus 1, it is simply taking the limit of each of the components. And so we can see that this is going to happen for us with limits and derivatives and integrals as well. It makes this a pretty nice and easy start to studying functions of higher dimensions. All right, we have a couple of examples to do here. Let's find the limit as t approaches 4 of this first function. So this function has 3 components: a square root of t minus 3, root t minus 2 in the numerator divided by t minus 4 in the denominator, and tan of pi over t. Now, usually what we would do when we do limits is put a 4 in. So let's imagine putting a 4 in. This is going to be the square root of 4 minus 3, so that's just equal to 1. That's no issue. This one is going to give us a little bit of an issue, because root 4 is going to be 2. 2 minus 2 on top is 0, and the bottom is also going to be 0. So we can imagine doing something like L'Hopital's rule, or this is one of those problems where we can just rationalize the numerator. So we have t minus 2 over t minus 4. And then let's multiply this by root t plus 2 divided by root t plus 2, and that will, quote, rationalize the numerator. And what we will have left there is a t minus 2, which let's call it a t minus 4, divided by t minus 4 times root t plus 2. So the t minus 4 should cancel, and you have 1 over root t plus 2. And then now we take the limit as t approaches 4 of this expression that got simplified. And so this is going to be 4 under square root. And so that's going to be 2, and we add 2 to it, and you get 1/4. So this just becomes 1/4. We have, for this last one, tan pi over 4. And if you can remember, that's going to be 1. So this is going to be 1. So our limit then will become this. This is your L is equal to, as in the limit vector of that particular problem. Okay. It's possible the limits might not exist depending on the situation that we have, but in this particular case, I think we found the limit. All right. Another problem for limits. Limit as t goes off to infinity. So again, we're going to take these limits one by one. Limit as t approaches infinity of e to the negative 2t. That goes to 0 if you imagine what the graph is going to look like, and if you go to infinity. Limit as t goes off to infinity of 2t plus 3 over 3t plus 1. If we have a polynomial over a polynomial, like a rational function, and they happen to have the same degree, then we simply look at the limits. Well, the limit is simply going to be the coefficient of those highest term in the polynomial. You can use L'Hopital's rule if you want, because this is going to be infinity over infinity, but it really just comes down to those coefficients. So this is 2/3. And then lastly, limit as t approaches infinity of the arctan function. So this is 2 times infinity, which is infinity, and you just have to remember the arctan function. Because of those asymptotes, the vertical asymptotes for the tangent, the arctan, which is going to be the inverse function, has asymptotes at pi over 2 as it goes off to infinity. As it goes off to negative infinity, you'll be at negative pi over 2, but that's not what we're looking at. Okay, so I think we have it here. Your limit L is going to be 0 for the first component, 2/3 for the second component, and pi over 2 for the third component. All right. So one more concept of the definition of a function to be continuous at a point. 3 things have to happen. The function has to exist at that point. The limit as t approaches that point of that function also has to exist, and then finally they have to be equal to each other. Okay, and generally we're going to be dealing with nice functions, except when we see things like rational numbers, or where the domains might get cut off. You might have some holes in the graph and things like that. So let's see. Let's take a look at this first problem where they ask us to find the limit as t approaches 0. So the limit as t approaches 0, let's write that out over here. Limit as t approaches 0 of e to the t, comma, sine t over t, comma, e to the negative t. Okay, the first limit and the last limit are pretty straightforward. You just put 0 in for t, and then you happen to get 1, positive 1 for both of them. Now this middle one, we need to take the limit as t approaches 0 of sine t over t. I think we've proven this at some point in our calculus careers. This thing approaches 0 over 0, so we'll use L'Hopital's rule, or I don't know if you remember, there was a story behind using this B for Bernoulli, and we can think about what that is later on. But we take the limit, or we take the derivative of the numerator and take the derivative of the denominator and then put in the value 0. And then as long as we don't have an indeterminate form, like 0 over 0 or infinity, then we have an actual value. So this is also going to be 1. So yes, the limit does exist, and L is going to be equal to 1, 1, 1. Now we want to know if the function is defined at that point. So let's take a look at the function and imagine putting 0 in for t. So e to the 0 is just going to be 1. Now this is going to be an issue because sine of 0 over 0, we saw that that didn't exist. We have a 0 in the denominator. So that's not going to work out. So the first and third components are okay. This does not exist here in the middle component. So we have to say that R of 0 does not exist just because of the middle term not existing. So dne for this, and then we have to conclude that because we don't have the list of criteria here satisfied, then we have to say that it's not continuous at that point. So our conclusion is no, not continuous. At t is equal to 0. Okay. All right, so that is our first section, section 3.1 in this chapter. Good luck.